My name is Jeffrey Frankel, and I have shown students techniques to reduce the time answer questions in paper 1 of the IB chemistry exam at both levels, standard level and higher level. These questions are multiple choice. You have 90 seconds available for each question, and you have no calculator. These techniques that I am about to show you will help you dramatically reduce the time needed to answer those questions correctly in maybe 30 or 40 seconds, and in some cases even less, thus giving you extra time to do other questions within the paper. When you see this curve, and these are the reactants and those are the products, according to that's the course of the reaction, you should immediately realize that this heat is being given out, and therefore it is an exothermic reaction. So you know it's either there, you're looking for exothermic there, and you're looking for exothermic in this one. At the same time, you know that it's exothermic and the products are more stable than the reactants. They have less energy in them, less chemical potential energy than the reactants, and therefore the products are more stable. So you're looking for exothermic, more stable. And you go through here and you see exothermic products more thermodynamically stable than the reactants. And that's the answer. If you look at the others, you will see that they don't make sense. The reaction is clearly not endothermic. The reaction is not endothermic. The reaction is exothermic, and the reactants are more stable. The reactants? No, the reactants are not more stable. This is one of those situations where certain words or phrases go together. Exothermic, products, more stable than reactants. And of course, the other important thing, heat is given out and temperature rises. So those things go together with exothermic and this curve. If you see the opposite curve, that's this one, where the reactants are here and you go there, and it's like that, then in this case, this is endothermic. This heat is taken in, and the reactants are more stable than the products. But in my experience, if you remember one set, say the exothermic set, just remember that, the exothermic set, products more stable, heat given out, then it's easy to realize what the opposite is, the endothermic set. Okay, so the word is exothermic, and we know exothermic means heat is given out. You only have to look at ice melting and you know heat is not given out when ice melts. Heat is taken in. So immediately you can say 1 is wrong. Every answer with 1 in it is wrong. A is wrong, B is wrong, D is wrong. Lo and behold, C is the only one that doesn't have ice melting. So it must be right. Let's look at that. If you didn't know it, you now know it. Neutralization is an exothermic reaction. Sodium hydroxide and hydrochloric acid, they do give off heat. If you've done a titration, even a fairly dilute sodium hydroxide solution and hydrochloric acid solution, and you've felt the conical flask underneath the burette, you'll realize that it gets warm. It may not get very hot, but it does get warm. Therefore, neutralization is always an exothermic reaction. And combustion, burning, by its nature, combustion is exothermic. So, yes, 2 and 3 are the correct ones. They are both exothermic. And ice melting, definitely not exothermic. Now we go to, on the opposite side, endothermic. Yes, the system absorbs heat. Yes, the enthalpy change is positive. Bond enthalpy total for the reactants is greater than the bond enthalpy total for the product. Yes, that is true. So all three are true for endothermic. Therefore, the answer is D. Right. Just to confirm this final one, I'll do this. This is, as we did earlier, the endothermic one. And there we have the system absorbs heat. Enthalpy change is positive. It goes from there to there. And the enthalpy total for the reactants is greater than the enthalpy total for the products. This is another question where the examiner is asking you, do you know the meaning of the word exothermic? You must be able to say, that is exothermic. All oxidations are exothermic. You need to be able to say that this is exothermic. All neutralizations are exothermic. A base and an acid, that is a neutralization, it's exothermic. And as soon as you look at this one, you realize that this is not exothermic because you will have to put energy into the chlorine molecule in order to break the bond. So therefore that one is endothermic. So you can see 1 and 3 are exothermic, 1 and 3. The answer is B. Interestingly enough, if you saw that that is not exothermic, you could say anything with 2 in it is wrong. A is wrong, C is wrong, D is wrong. Okay, when you look at this, you must immediately think of the equation Q equals mc delta T. Maybe you don't need to write it down, but you must immediately think of it, and they have told you that the temperature increases by T. So delta T equals T. And they've said the mass is m and the heat capacity is C. So therefore the answer is A. And I think it's clear from this question that the formula they're expecting you to use is Q equals mc delta T. If you have any doubts, as soon as you see this phrase specific heat, then you know it applies to this formula. This formula is the only one within IB chemistry that has the variable specific heat in it. So, as soon as you see the word specific heat, you know it's this formula. And sometimes the word specific heat is not included, but you can guess that it probably is this formula because they talk about mass of a substance, temperature change, and joules of heat energy, or kilojoules of heat energy. Anyway, going to the formula Q equals mc delta T, and they're asking how many joules. So this is the unknown, and they have to give you all the others. They give you the mass, which is 2. They're giving you the C, which is 0.9, and they're giving you the delta T, which is 30 minus 25, which is 5. And so the answer is 9, which is A. Here is another one using Q equals mc delta T. Now you don't have to write the formula down if you think you can handle it without writing it down. I mean, the temperature is 10, so delta T equals 10. The quantity of heat is 2 times 10 to the 2. I put that down as 200. For me, it's just easier to see it. A number like 2 times 10 to the 2. So much easier to see it as 200. And what is the specific heat capacity of the substance? 5 grams is the mass. So the unknown is C. And that's clearly C equals 4. That's that one. Okay? And this is something that can simply be done in your head for some people. Notice that there are 4 variables within the equation. They will in general give you 3 of them, and you're expected to find the 4th. So it's not a particularly difficult problem. Now, this is one which causes students problems. They think that they have to do 4 calculations. There is 4 specific heats, there's the value of Q they give you, and there's the value of mass. And you're expected to work out the temperature change. Now, if you think about it, you don't really need to do all 4. You only need to do any 2 in order to find the trend. And in fact, the most obvious 2 would be AU and copper, the copper one. However, you don't even need to do any calculations. As soon as they give you a lot of numbers, all those 4, this one there and that one there, you need to think, maybe I don't need to do so many calculations. And if you look at the formula, Q equals mc delta T, they tell you what Q is, they tell you what M is. Therefore, you can say Q over M equals a constant. Again, you don't have to write this down. Equals C delta T. In other words, the product of C and delta T is fixed by the value of Q and M. It doesn't matter what the value of Q is, it's the same for all of them, all 4 of them, and it doesn't matter what the value of M is, it's the same for all 4. Therefore, Q divided by M is a constant, therefore C multiplied by delta T is in itself a constant, that product is constant. Now, this is more of a mathematics problem than a chemistry problem, because from there you can simply see, well, what is the value of C when the temperature increases? If the temperature increases, the value of C must go down. So therefore, to get the highest change in temperature, I need the lowest value of C. What is the lowest value of C? AU. There it is, C here, AU. What I would like to talk about now is to show you that if you looked in the data booklet, and I've got the particular page here, that the physical constants and unit conversions, and you look at specific heat capacity of water, you find it's 4.18, which is fine, and they give you this unit there, and in brackets they give you this other unit. And you see that it's kilojoules, kilograms, joules, grams. And the difference is nothing more than 1,000 J over 1,000 G. So when you're looking at kilograms, that's 1,000 G. When you're looking at kilojoules, that's 1,000 J. And so if you cross those out, you get J over G, which is this, J over G. Kilojoules over kilograms is the same as joules over grams. So those 2 units are the same. It's important to realize that, because when you're doing the equation, Q equals mc delta T, it's important to realize that if M is given in G, then the Q would be given in J, joules. If M is given in kilograms, then the Q would be given in kilojoules. So that is important to know that. And it's just important to be clear about the constants. You can use that or that, it doesn't matter. But when you're doing the equation, you have to be consistent. Going back to this, you will see that they've used a slightly different unit. Instead of J, G minus 1, K minus 1, they've used J, kg minus 1. In other words, they've simply multiplied the heat capacity by 1,000 in order to get this. So normal heat capacity would be 0.385 for copper and 0.234 for gold and 0.234 for silver, 0.234 for silver, 0.130 for gold and 0.134 for platinum. What they've done is multiplied the grams by 1,000, and therefore they've given the final result. The C has increased by 1,000 in each case. And the reason I'm telling you is this is just to be careful with this, with the units that they offer in an exam. This is a question about the meaning of various words and what happens with respect to energy when you're breaking a bond and when you're forming a bond. Now, I'm somebody who remembers that breaking a bond is like breaking a pencil. You have to put energy in. If I put this pencil here and I want to break it, then I have to put energy into breaking it. So I look at the endothermic point of bond breaking. Bond breaking is an endothermic operation. You put energy in. It's also delta H positive. So that is clearly where I see bond breaking. And lo and behold, bond formation is clearly exothermic. In other words, heat is coming out. And delta H is negative. So immediately I would say C. Basically, I started with the pencil. I'm breaking a pencil. I need to put the energy in. And therefore, I look for endothermic in bond breaking. And delta H positive, therefore exothermic is bond formation, and it's delta H negative. In this one, you simply have to know what is the definition of bond enthalpy. Bond enthalpy is the energy needed to break 1 mole of a bond into its gaseous atoms. And the only one that fits that is B. There's a gaseous hydrogen atom, gaseous chlorine atom. Ignore those with ions because that's not involved. Ignore the molecules and ignore this last one. Okay, so this is the only one that fits with the definition. This is a little bit more complicated than the last one, but not impossible, because if you look at it, then the only way that the hydrogen bond is broken and fits within the definition we've just discussed is this final one, D, because it's got nothing to do with breaking into 4 bonds. This breaks 4 bonds. This one also breaks 4 bonds. This one breaks 4 bonds. This is the only one that breaks 1 bond. Okay, you're not told everything about bond enthalpies. You're not told anything about the HO bond enthalpies. But there's 2 of them. There's one there, and they occur on that side of the equation as well. So you don't need to include them. All you're interested in is the OO, and the half O double bond O. So that's the only thing you need to consider. And the OO single bond is 146, and the half of that goes to a half 496. And it's simply the sum of the reactants, in this case just the 146, minus the sum of the products, in this case half of 496, which equals minus 102. Now there are 2 ways of thinking of the calculation. You either remember it's a sum of reactants minus the sum of products. That's one way. Or you simply remember that bond enthalpies are always positive, and so in this case you're putting energy in, you're breaking bonds. If this was a question 2 paper, you'd write it down. Breaking bonds plus 146, and making bonds minus half times 496. So there's two ways of doing it. You either do the sum of the reactants minus the sum of the products, or you write down breaking bonds minus making bonds. This one is done in a similar one to the previous one. The hydrogen peroxide goes to water plus oxygen one. Some students have seen all these numbers and they think, oh, they have to do the full calculation for bond enthalpy. Then they come to a problem. The C bond is not given to you and you don't have the tables. The reality is that most of this, put a 2 there, is repeated over here. So this again is something like a CH plus ClCl goes to CCl plus HCl. You don't have to bother about the CH3, CH2, CH3, CH2. It's just the sum of these two minus the sum of those two. So what is CH? That's plus 413 ClCl, and they put it in order for you as well. 2, 4, 3, that's plus, and then so it's minus CCl 3, 4, 6, and there's the 4, 3, 2. And if you look at it, quickly look at that, that's 640 minus 770 approximately. It's minus that one. Without doing the exact calculation, it must be minus 122, because we know it's not that, and this is just 2 negative. So just by eyeballing that, you can see it's B. You can, of course, do the calculation if you want to, but it is B. Okay, there's a lot of information in this question. It does take you time to read it, but essentially you're trying to determine the delta H for this equation, and you're given these 3 other pieces of information. The way to look at it is, okay, see there, so I'll add that equation in, so minus 390, that is 2H2, I'll add 2 of those equations in, plus 2 times minus 286, and then there's this one. Now, this one has the CH on that side, but on there, it has it on the opposite side. So whatever is the sign of this reaction, I will reverse it. So I add the opposite sign, 890. It's going to be this, B, minus 72. Okay. There is more than one way to do this one. However, what I'm going to show you is how it looks from the point of view of 1.5 logic, or what I think is logic. SO3. So sulfur goes all the way to there, and it's SO3 and 395. So sulfur is oxidized all the way to SO3, and it's minus 395. Here, that one, sulfur plus O2 goes to SO2, and that is the unknown, H unknown, and then the SO2 plus oxygen, it's a 0.5, half a mole of oxygen, goes to SO3, and it's minus 98. So you can see from a logical point of view, the combined reactions must produce a delta H of minus 395, and here part of it produces already delta H of minus 98. So this must be a delta H of minus 297 approximately, and there it is, 297 there. You just look at those figures to see which one fits in. The positive one doesn't fit in, that's too big, and that's the positive one doesn't fit in. So only that one fits in with that to produce that number. And here it is. here it is, the very one I was talking about. Carbon plus oxygen goes to CO2, and that's minus 394. And what they give you is, or what they're asking for, is C plus a half O2 goes to CO. That's what they're asking for. And CO plus a half O2 goes to CO2. And they're telling you that's 283. 283. Therefore, this must be the difference between those, which would be approximately minus 111. You simply look at this and you know it must be negative, and it must be this small one. That one's ridiculously high. So, if you get these kind of three equations together, with sulfur and oxygen, carbon and oxygen, carbon dioxide, SO3, SO2, carbon monoxide, etc. Get those kind of equations together, you can quickly do it in this way, which is a version of the Hess's law, really. And there are some others that examiners throw at you which are very similar and can be treated in a very similar way. There is more than one way of doing this one. The examiner is looking whether you can handle these variables x and y. Let me show you one way that I would use. I would start with this equation as the top one, Ca plus 0.5O2 plus CO2 goes to CaCO3. And then I would put the two that make up this one underneath it. So I would go to Ca plus O2, and there's two of those, goes to 2CaO, and then I go to this one, which is CaO plus CO2, goes to CaCO3. So this is a question about Hess's law, and they tell you information on this one, which is plus y. They give you information on this one, which is plus x, and this is the one they're asking. What is the delta H for this? You can see that y must equal that plus that. So y equals, now it's not actually that, it's half that, half x plus delta H. Therefore, delta H equals y minus 0.5x, which is A. Okay, so that's one way of doing it, and I've done this with carbon and oxygen going to carbon dioxide, and with sulfur and oxygen going to sulfur trioxide. The second way of doing it is simply to look at each of these and say, I've got a CaO there, so I've got it's on that side, and this CaO is on the other side. So first of all, I've got to halve it, and then I've got to make it negative, so it's minus half x. And then you go over to CaCO3. That's negative, and that's on that side, that's on that side, so they stay there. And that's y, and and you ignore the CO2. You don't need to have anything for the CO2 because that's already included in the CaCO3. That's included in the y, and you know that the final result is the sum of the reactants minus the product, so it's y minus a half x. In this case, the examiners are giving you the delta H of formation of three of the substances involved. The delta H of formation of magnesium is 0, so you can ignore that. The thing to realize is that they use this phrase flash photography. Now when you do energetics, we talk about exothermic reactions being the giving out of heat. But in addition, they can be the giving out of light, and this is what happens in this particular reaction. It does give out heat as well, but it gives out a lot of light. And this is clearly an exothermic reaction. Therefore, know that the relevant enthalpy change of this reaction is going to be negative. So it's either this one or that one. You can forget the other two. So let's look at the delta H's of formation of that and those two, and take into account that you do the delta H formation of the products minus the delta H of formation of the reactants. So the delta H of formation of the products is 3 times that, minus 3 times 602, plus the KCl, which is minus 437, minus the delta H of formation of the reactants, which in this case is KClO3, and that's minus 391. So a minus times a minus makes a plus, and this is 1800 minus 1800 plus 437, approximately, plus 391. And you can see it's minus something like 1800 or so. So immediately you go to that one. You don't even have to calculate the exact number there, because it can only be that one. It can't be this one. Thank you for watching. If you found this YouTube video helpful, please see my other YouTube videos. Thank you.